Bismillahirrahmanirrahim and welcome all students to the new lecture, and this is a knapsack problem. Here once again I would like to repeat that we are not going to study knapsack problem for the sake of the solution of knapsack problem. As I have been repeating it again and again, we are studying knapsack problem to understand how can we apply or implement a dynamic programming approach to some optimization problems. So knapsack problem, you are familiar with this term. Uh, Previously we did a fraction knapsack problem in the greedy algorithms where we were applying greedy approach. Today we are considering another version of knapsack problem, that is 0-1 knapsack problem, or you may call it the binary knapsack problem. We can understand knapsack problem as if we start thinking about some thief and mm, just a thief breaks into a museum where the fabulous paintings and sculptures are um, presented for the audience, but the thief wants to pick the most costly items from that um, what we call in the museum and put them in the knapsack. He has one knapsack with him, and he wants to fill it as much as possible based upon the capacity of that knapsack. But due to the the type of the item, the items cannot be broken, just like we did in the fraction knapsack. So he has to either keep the whole item in his knapsack or he has to skip that item. So this is how we define it informally, knapsack problem, 0-1 knapsack problem. So the question is, what items should the thief take to maximize the haul? So he wants to maximize his profit. Before going to the formal definition of the of 0-1 knapsack problem, let's look at few terms that are being used in this definition. Like W represents the maximum capacity of the knapsack. S is the set of n items, where item is represented by I. Weight of I means the weight of ith item. B of I represent the benefit of ith item, and all these numbers are integers, so it means there is no possibility of breaking the item, or the cost cannot be in fractions. So the problem definition now comes: how to pack the knapsack to achieve maximum total value of the packed items. To understand and visualize the knapsack problem, let's as flashed is the instance of a knapsack problem where there are five items and the weights of on the items, and along with that what the benefits of those items. And on the left side, in the light blue color, there is a knapsack with a capacity of 20. This is another way of defining the knapsack problem. This is the same thing. You can just stop and go through this slide when you would be listening this video. We can define this problem mathematically as shown in this equation. We need to maximize the benefit of all the picked items subject to the weight of all picked items that should be less than equal to the total capacity of the knapsack. Let's start the solution of this problem with the brute force math approach. We can simplify the all possible solutions, and that would be 2 raised to power n, and with all possible combination filling the knapsack to the maximum of w as much as possible. So it is possible that they left some empty spaces, that was not possible in the fractional one. The question is whether we can improve this time complexity, that is 2 raised to power n, or not. The obvious solution answer is yes. With the algorithm based on dynamic programming, we can improve this one, but before that, we have to find out the subproblems. We have to identify the subproblems. Let's try this one. So finding a subproblem from the set of items that are labeled from 1 to n. Let's assume that we have a set sk with the items labeled from 1 to k. That is the subproblem. So and what we have been doing is that if sk is the solution of a subproblem, then Sn would be the solution of the main problem, having Sk as the part of that one. Let's define the subproblem formally. If items are labeled 1 to n, then a subproblem would be to find an optimal solution for Sk, where Sk is the solution as of a subproblem from items labeled 1 to k. This is a valid subproblem definition. If you can recall a small figure or two rectangles on the right top corner of the board, we have been drawing again and again. So this truly maps on that figure. The question is, can we describe the final solution S of n in terms of the subproblems? Okay, its direct answer is, if you think about this one, the answer is no. And in the next slide, I will be explaining that one, how this answer is no, while we have been doing that one. So this is a little bit different from the previous problems. Let's have another this data set. This is the old problem we discussed in previous slides. And here the subproblem is from 1 to 4, and we pick all the 4 items to maximize the profit that still remain under the capacity of 20. So total capacity used is 14 and total benefit gain is 20. When we go for the S5, that is the solution of the whole problem, so we see that the solution is not having second problem in it. So it is carrying problem 1, it is carrying item 1, item 3, item 4 and item 5. So the maximum capacity being used is 20 and profit is 26. And we can see that this subproblem is not the part of this problem. Now, the solution of S4 is not the part of the solution of S5. So that is really clear here. So it means we have to find something else. We have to add another factor because the capacity is there. So every sub item, every what we call sub-solution or optimal substructure should also be having some information about the remaining capacity of till that moment. As we have seen, the solution for S4 is not a part of the solution of S5, so our definition of a subproblem is flawed and we need another one. Let's add another parameter, that is W, which will represent the exact weight of each subset of items. The subproblem then will be to compute the B of K comma W. So that means the overall benefit for K items and W remaining capacity. The mechanism is very simple. Either we will be picking an item or we will be dropping that one. So there would be benefit with that item or without that item. And in the same way that there would be capacity with that item or without that item. So just like this is the same problem. So we have capacity 20 and we have 5 items. So taking the decision about item number 1, either we pick it yes or we will not pick it no. If we pick item number 1, then the remaining capacity would be 18, and if we pick item number and the remaining items would be item number 2 to 5. If we do not pick item number 1, the remaining capacity would be 20 and the remaining items would be 2 to 5. So in this way we have to go beyond this one for the item 2. So these 4 branches would be for the item 2, either for the yes and no, and this way this would be exploring all possible scenarios of picking the items in all possible combinations, and that would be 2 raised power n. So that is now that is the exact recursive formulation of this problem. We can define formally as a recursive function or recursive relation, like benefit of k comma w would be benefit of k minus 1 comma w if weight of that item is greater than w. So that means the old solution would be the current solution if you cannot pick the current item. In the same way, if this is not the scenario, if you can pick the scenario, so then you will find two solutions, and out of those two solutions you will pick the solution that would be giving you the maximum benefit. That is, whether you pick the uh, item. So if you pick that item, then the benefit of that item will be added, and if you do not pick that item, then the previous solution would be the current solution. So this would be the previous solution, and if you pick the item, then the kth item's benefit is added in the k minus 1th item, where the remaining capacity would be w minus wk. It means that the best subset of sk that has total weight w is one of the two. The best subset of sk minus 1 that has total weight w, that is the first scenario, and the best subset of s of k minus 1 that has total weight w minus k plus the item of k. That is this one and this one. So which one is the best will be picked with the maximum function. Seen in this equation, so there are actually two scenarios. And number one, the item weight is more than the remaining capacity, and number two, when the item weight is less than the remaining capacity, and you can pick it. And but in that scenario, you will either pick the item or you will not pick the item. You will check both the scenarios. Whichever gives you the best benefit, you will pick that one. So just just have a look at this slide. Go through this text. Stop the video and go through this text carefully. Before I go for the algorithm, I would like to explain how the recursive formulation uh, we can find the memoization or the memory required for that algorithm. I will be explaining it verbally because we have already done a couple of problems like rod cutting and longest common subsequence problems. Finding all possible unique references from the tree, you can find that there would be two parameters of every reference. The first one would be the capacity and the second one would be the item. So all references of all items are there, and almost every weight capacity that ranges from 1 to w would be there. So that means we need a two-dimensional array, that is w into n. N is the number of items and w is the capacity. So this is what we need, and just like LCS, we need to fill first column as zeros, second column as first row as zeros, and then ranging from 0 to w, we will be checking whether the uh, item weight is less than the capacity. If it is true, then we will go for the calculations, that we are here basically applying the maximum formula, whichever is, if this one is, if picking the item gives you the benefit over not picking the item, then you will pick the item and store it in IW. And if not picking the item gives you the benefit, then you will not pick the item, and previous solution would be the solution of the current problem problem set, or subproblem, whatever you call it. No. We will run this algorithm after this slide. First of all, we look at this algorithm. So this is a loop, this is another loop, this is another loop, and there is rest of the algorithm down here. So we see we have to find what is the running time of this algorithm. So it is obviously big of n into w. So w for the first one, this is w times loop, and it is going to repeat for n times. So this loop is for n times and this loop is for w times. So it makes it n into w times. Going towards the final stage of this lecture, let's solve an example. So this is, there are four items. Total capacity is of knapsack is 5. The data set is, if the weight is 2, the benefit is 3, the weight is 3, benefit is 4, weight is 4, then benefit is 5, weight is 5, and benefit is 6. So first of all, we draw a n into w times matrix, just like this one. And now we are going to fill the column one by one. So this is what we have to do. And now we are going to fill the first row, and it is having the meaning that if your capacity is 0, then whether the item is 1 or 2 or 3 or 4, your gain would be 0. You cannot get any benefit out of that one if you are having a knapsack that is having 0 capacity, so you cannot pick an item. So that's why these greens are there. Now moving toward the main part of the algorithm. So now first of all, try to understand. So this is on the right top corner. You can see there are four items with the uh, weight and benefit set. Okay, so this is the execution of the algorithm for weight is equal to w1, w is equal to 1, so benefit is equal to 3, and I is equal to 1. So we are going to fill this cell. Okay, so this one. So item number 1, its weight is 2. So that means you cannot pick this item. You cannot put this item into your knapsack. Your knapsack weight right now is 1. So it means the previous solution would be the current solution. Like, so now 0 is the current solution. Moving towards next item. So now we are now the capacity, we have increased the capacity of the knapsack, that is 2 now, and we have only one item that is in below 1. So whether we can pick it or not, yes, we can pick it. This is 2 and this is again 2 here, the weight of the knapsack. So we can pick it and we can get the benefit of 3, and we will check whether there is a space left behind or not. If we find any space left behind, then we find its optimal solution from the last column, and we add it with that one also. So right now, because this is basically the optimal solution of the remaining knapsack, or you are filling it with 3, so it is actually the 3 plus 0, and answer is 3. So because after adding this item, that is 2, they left 0 capacity, so you go for the 0 row and add the worth from there in this 3. So 3 plus 0 is 3. Remember this one. It is not only 3, it is 3 plus 0. Okay, now increasing the capacity of the knapsack to 3, we will go for uh, this is 2, so we can add 2. So the benefit is 3, remaining capacity is 1. So it means we are going to add this 0 in the 3. So 3 plus 0 is 3 again here. So look at here, this one is 3 plus 3. In the same, we go for this one. So remaining capacity is always 0 because whether you have it or not, you are having the profit is 0 of the optimal uh, solution. Now you have two items. So we are going to fill this column now. You have two items and your total knapsack capacity is 1. So neither of the two items can be added to the knapsack. So we will see that remaining capacity is 1. So you will pick 1 from here from the previous column and will this one, that means the old solution is the current solution. So here 0 is here. Now you have the knapsack capacity is 2 and you have two items, that is item number 1 and 2. You can see that item number 1 can be adjusted with a remaining capacity of 0. That would be this item 0, value 0 would be added in that one. The solution is 3 plus 0 is 0. Okay, so now next is your remaining capacity, your knapsack capacity is 3. You can either add 2 or add 3. So adding, so only you are picking this item number 2, that is 3 here. Either you can pick it or you cannot pick it. So you have to make a decision about the item number 2. So you can pick it, it will give you benefit 4, and if you do not pick it, then the benefit would be 3. So picking item number 2 would be more advantageous. So like this one, this is 4 plus 0 is added. Okay, so in this way we can add this one. Okay, now coming up to this one. Now item number 3, we can pick it. The remaining capacity is 2. We will go to the row 2 and pick the 3 from the last column. So it will become 4 plus 3 is 7. So do fill these two columns carefully. I just uh, move the animation. Keep on doing. Think about it, how these items are being picked. So it means you have picked the fifth item. So that means the previous solution is the current solution. 0, the previous solution, again previous solution, again previous solution, and again here you can see the previous solution is the current solution. Yes. So this is how, so this is the end of this animation. Few things you have to do and you have to calculate yourself. This algorithm only finds the maximum possible value that can be carried in the knapsack. Just like in the longest common subsequence, you find the answer in the bottom right corner. To know the items that make this maximum value, in addition to this algorithm is necessary. Just like the arrows you have been marking in LCS, so some mechanism like that one is required here too. So for that you have to look at the LCS algorithm and you have to do that on your own. So guys, if you have any queries, do mention me in the comments and give me the feedback about your about this lecture.